Hi, I'm Professor Waldron's avatar and I'm here filling in for him today. We're going to talk today about probability distributions and applications after last week where we talked all kinds of things about probability without actually getting into their distributions. I'm not going to stick out on the rest of the slides just because I don't want to get in the way of stuff. We're going to have a quick review of properties of probability that we covered last week, and then I'm going to apply these with a couple of important examples of the normal distribution and the binomial distribution. And you can follow up with this with extra readings from your textbook in Chapter 3. Recall properties of probability starting with mutually exclusive events. If A and B are mutually exclusive, then it means that you can either have one or the other, but not both. For example, having cancer or not having cancer, you either have it or you don't have it. And in the event terminology, where something is one thing or the other, you can either have one or the other of these conditions. And for mutually exclusive events, the probability of the union of those two things is the simple sum of them, because these options are mutually exclusive, and in this case they sum to 1 because they're also exhaustive of all the possibilities. And the intersection probability of cancer and not cancer is 0, or in other words, the overlapping area of these two circles is 0 because they are exclusive. For non-exclusive events, such as having cancer and having heart disease, there is an intersection or some area in the middle of this Venn diagram. And in this case, the probability of the intersection, so cancer and heart disease, is the sum of the probability of cancer, enclosed in this circle, plus the probability of having heart disease, minus the probability of having both, this intersection in the middle that we've counted twice. And if these are independent events, then that intersection probability is equal to the product of both events. So the product of having cancer and heart disease would be equal to the probability of having cancer times the probability of having heart disease. And that is if they're independent. If they're not independent, then it is not just the probability, let's say, of having cancer, but the probability of having cancer conditionally on having heart disease times the probability of having heart disease. And this, of course, could be written either way, with also the probability of heart disease given having cancer times the probability of cancer for non-independent events. A nice little cheat sheet for you here of the notation that we have learned and that you should know. I won't go over it all here, but this is just so that you have it in today's notes as well. A random variable is any characteristic that can be measured or categorized where any particular outcome is determined at least partially by chance. A couple of examples would be the number of new diabetes cases that will be seen in diabetes in New York City in any given year, or the weight of a randomly selected individual in New York City, where you don't know the answer, but there is a probability of any particular outcome occurring. And the major types of random variables are, one way to categorize them would be as categorical random variables, discrete random variables, or continuous random variables. Pursuant to the notation that I gave out in the syllabus, I will notate random variables using uppercase Roman letters and particular realizations of those random variables in corresponding lowercase letters, and with particular realizations given a subscript such as x sub 1 sub 2 for a corresponding random variable capital X. So an example of a categorical random variable is, well, I've given you the answer here, but the Landsteiner blood groups, where in the population, the approximate prevalences are these percentages, and for the proportion that you actually observe in any group of people would be a categorical random variable. The number of visits to an obstetrician's office during an uncomplicated pregnancy, given these hypothetical fractions, 0 visits, 20%, 1 visit, 20%. This would be an example of a discrete quantitative variable. So it's quantitative, recall, because rules of arithmetic can be applied. You could add and subtract these. However, it's discrete because you can't have just any value. They must be integer values. The distribution of body mass index in a population would be an example of a continuous variable if it is measured with decimal places. And this is a visualization of that probability distribution. With a maximum probability somewhere around 25 and decreasing off at either end as a continuous random probability distribution. So the first thing to know about continuous random variables is that any finite interval within the bounds of that probability distribution will have a positive probability. And that probability, if you are looking at a probability density plot like this, is the area under this curve. What is the total area under this curve if you went over the entire range of the possible values of the distribution? It would be 1. And for any finite interval within those possibilities, it would be greater than 0 and less than 1. And you'll be doing some calculations like this once we start hypothesis testing, because the null distributions that we will use of test statistics will have a known probability distribution, and you will be calculating the area under tails of curves like this to calculate the probability of an event happening by chance. So again, in general, we will be interested in intervals along these curves, in particular in the tails of the curves, and counting up the total area or probability of intervals of those curves. And once again, the interval containing all possible values, so certainly from -infinity to infinity, sometimes more restricted than that, but we'll have probability equal to 1. The two most important probability distributions for this class will be the normal distribution, this bell-shaped curve, and its cousin, the t-distribution, and for binary outcomes, the binomial distribution. And we'll be doing plenty of testing and calculation of probabilities with both of these. The normal distribution is applicable in a lot of different instances of continuous random variables, and the binomial distribution is applicable in instances where the outcome is binary, either yes or no, healthy or sick, and we have a number of independent events. It describes the probability of the numbers of yeses and nos in those independent events. So the normal distribution, this symmetric bell-shaped distribution, is characterized by 2 parameters. And I'm giving the population parameters here, mu for the mean, and sigma, the population standard deviation. The mean defines the center of the normal distribution, and the standard deviation defines the spread of it. So here are just a few examples. This curve here has a mean of 0. It's centered on 0. and a relatively small standard deviation of 0.2. These three curves here all have a mean of 0, but the second one, the green one, has a standard deviation of 1. Sorry, these are the squares of the standard deviation, the variance. And this third one has a variance of 5. So you can just see how increasing the variance increases the spread of this bell-shaped distribution. And the fourth one has again a variance of 0.5, but is shifted over to the left by a negative mean. A real-life example could be the heights of men and women, where men have a mean height of 70 with a standard deviation of 4 inches, and women a mean height of 65 inches and a standard deviation of 3.5 inches. So you see a bit of a shift and a slightly but pretty similar variance. So different peaks, but quite a bit of overlap between these distributions. So almost all of men's heights fall between about 60 and 80, and almost all of women's heights, according to these distributions, fall between 55 and 75, but there's a fair bit of overlap between those, which can be roughly described by this very handy to remember empirical rule of normal curves. It says that the one standard deviation above or below the mean contains 68%, approximately 68% of the probability. It contains an exactly calculable amount of the probability, but it rounds pretty close to 68%. Plus or minus 2 standard deviations contains 95%, and plus or minus 3 standard deviations contains almost all of the probability, 99.7%. So if you have a normally distributed random variable, its probabilities for a large sample or for the population will fall according to this distribution defined by the normal. So for that, heights of adult women with a mean of 65 inches and a standard deviation of 3.5, just applying this empirical rule tells us that 68.5% fall within 65 plus or minus 3.5 inches, 95% within twice that, and 99.7% within 3 times of that. So this is a calculation you can do very quickly without having to refer to probability tables or using software to calculate probabilities of the normal distribution, if it happens to be on these convenient values of 1, 2, or 3 standard deviations. So what about this instance, though? Getting a little bit more complicated here. What proportion of women are less than 68.5 inches tall? So that is from 1 standard deviation above the mean all the way to negative infinity, or let's say to a height of 0, so to the shortest women. It's a little bit more complicated in this case, but we can do it by adding things up in pieces. So the empirical rule told us that this part between -1 and 1 standard deviation contains 38% or 68% of the probability, and then the part outside of that must contain the complement, which is 32%, half of which is to the left. So 68 plus 16 equals 84%. So we can kind of break up areas under this curve and add them up. And you may need to do this for certain probability calculations for hypothesis tests. Z-scores are a standardization of the normal distribution, so it's sometimes called the standard normal distribution. And every normal distribution can be standardized simply by subtracting the mean, so you get a 0 mean, and dividing by the standard deviation, so that the standard deviation becomes 1. So all measurements, if we were talking about heights, it would have been subtracting the mean height and then dividing by that standard deviation of 3.5 inches. And after you do that, the distribution will follow the standard normal distribution. So there are many normal distributions with all different possibilities of the mean and standard deviation, but there's only one standard normal distribution. It has mean 0 and standard deviation 1. And observations, like the heights that are transformed using this equation, are called z-scores. The shapes of these distributions, any particular normal distribution and the standard normal distribution, are exactly the same if you change the scale on the horizontal axis. So the bell shape is the same. It is just the location of the center, so it's changed here from 60 beats per minute heart rate to 0, and the width of it is changed as well from a width of plus or minus about 40 to plus or minus just 3, but the shape is the same. Z-scores are useful because it makes it easier to compute probabilities from a table. And in the back of your textbook in Appendix 3.1, there's what it calls a normal probability table, which gives you the area in the left tail. So you can, if you know that an observation came from a normal distribution, or you're assuming that, you can convert it to a z-score and calculate the probability of observing it by looking that up in this normal probability table. So as an example, let's find the probability that a normal random variable takes on a value of less than 1.43 standard deviations above the mean. So this is a z-score. It's been turned into the number of standard deviations above the mean. Its z-score is 1.43. So let's look at that. Going down here, z-scores from 0, 0.1, 0.5, 1. Here's 1.4. And following to 0.03, I see 0.92. And so using this nice picture that they give us here, it shows that this is the area to the left of this particular value of z is 0.9236. So this probability is 92.36% that a normal random variable takes a value less than 1.43 standard deviations above the mean. Now, the table doesn't directly tell us the probability of the variable taking a value greater than this, but because you know this property of probability of mutually exclusive events, z can only be either less than or greater than 1.43, and you know that mutually exclusive exhaustive events have to sum up, their probabilities sum up to 1, then the probability of z being greater than 1.43 is just 1 minus the probability of z below 1.43, so 0.0764. So by remembering this rule of mutually exclusive and exhaustive probability events, you can calculate the other area that's not given by the table just by calculating 1 minus the alternative. Here are just a few handy z values to have. The one that you in fact use all the time is this probability of z greater than 1.96 being 2.5% or 0.025. That means that the probability of being either greater than 1.96 or less than minus 1.96 is 0.05, and we use this for calculating p-values from a normal distribution. As an aside, you can use the norm.dist function in Excel as a handy way to calculate p-values. Just to give another example here of using the z-distribution, what is the probability that a normal random variable assumes a value within 1.43 standard deviations of mu? So this is what the value that we looked up in that table, that 0.9236, but we don't want the entire left side of that. So we only want this middle part. And one way to do this is by first taking the area that comes less than 1.43 and then subtracting what would be to the left of minus 1.43, which is that 0.9236 that we looked up minus the 0.0764 that is the tail probability we calculated. It's the same as the tail probability on the left to give us 0.8472. And as an alternative, we could have just started that way and started with 1, the total probability, minus 2 times this tail probability of 0.0764 to get the same answer. So when you're asked to find probabilities using the z-distribution, you will have to do this, and you'll have to do it for other distributions as well. I suggest that you start by drawing out the normal curve on a piece of paper and shading the area corresponding to the desired probability. This will help you to make sure that when you look things up on the table, you know what they correspond to in a more intuitive way, and you can figure out how to make the calculations that you need from what you're able to look up on the table. I'm going to skip over those examples. You'll have plenty of examples to work on later in the lab, but do take a look at them. So, to solve some of our problems, we'll need to find the value of z that corresponds to a certain cumulative probability. So rather than what we did of starting with the value of z and calculating the probability, we have the probability and we need the value of z. And to do that, you can just use the table in reverse by finding that probability in the table and reading off the corresponding z-score. Or in software such as Excel or R or SPSS, you can use these are so-called quantile functions. So for example, to find the value of z for a cumulative probability of 0.025, you find 0.025 in the body of your table, and you will find, let's see if I go back here, 0.025. I'm actually not going to find that because this only starts at 0.5, but I can find 0.975, which is going to be, let's see. Sorry, I need the next page. It's not on here. You do have more values than this in your textbook, but I don't actually have this going up to 1.96, which is the answer. To find probabilities for normally distributed random variables, here's a set of steps you can take that'll get you through any problem that we can throw at you. First, you state the problem in terms of your random variable and the realized value. So, such as I want the probability of the random variable x being less than a particular value x. Then standardize x to restate the problem in terms of the random normal variable z, so the probability of z less than x minus the mean over the standard deviation. Draw your picture, which will show you whether you're looking at a negative z or a positive z, and then finally find the area under the standard normal curve, either using a table or your software. What about the binomial distribution? So we're going to talk now about binary variables and use the binomial distribution to describe repeated independent events that can only have two possible values, such as a coin flip or such as having cancer or not having cancer. And this single event is also sometimes called a trial, and the series of events is also sometimes called a Bernoulli trial. So for example, what is the probability that among 100 randomly selected individuals in New York City, 60 of them have private health insurance? So for this, we can use the binomial distribution to calculate those probabilities. You can only use them under these three conditions. First, that the trial has exactly two possible outcomes, and we will refer to these as success or failure, regardless of whether that is really what they mean. They might mean yes or no, but you need to for constancy and using this equation, decide which is going to be a success and which is the failure. Each trial must have the same probability of success. So these are, for example, the probability of having cancer for the number of positive cases in a group of people to follow a binomial distribution. Each person has to have the same probability of a success. And finally, these n trials are independent. So the probability of having a success on one trial does not depend on any of the previous trials. And if these three things hold, then that probability of x successes in n trials, where each of those trials has a probability of success p, is given by this equation, which is the binomial distribution. And in here, the exclamation point is a factorial, which you can calculate on a spreadsheet or using the binomial distribution in your software. I have also given you a binomial distribution calculator with your notes that you can use for calculating this distribution. What does it look like? Well, it turns out that it looks not entirely unlike a normal distribution. And what I'm showing here is for trials of several different sizes. So in the red on the left here is a trial of size n equals 20 with a probability of success in each trial of 50%. So this is a coin flip. What I'm saying, if this is a coin flip, that if I flip this coin 10 times, my probability of getting anywhere between 0 and 20 heads, which are all of the possible values, follows this distribution. And if I repeated this so-called Bernoulli trial many, many times, this is the distribution of heads that I would see if I looked over these repeated trials of 20 coin flips, with the most probable outcome being 10 heads out of 20, because the probability of a head is 50%. Now, if I go up to 100 trials, so in the green on the very right here is the distribution of successes or heads for a probability of 0.5 and 100 events. So the most likely outcome is 50 successes. And you'll notice there's a somewhat wider distribution here than there was when there were only 10, and that makes sense because there are a lot more possibilities for the outcome. And then finally, for the same sized n of 100 with a reduced probability, so a weighted coin if there is such a thing, with the most likely point being the probability of success of 30%, you just see a shift. So this does look something like a normal distribution with a mean and a standard deviation. And we'll get back to that. But as an example, the prevalence of diabetes in some elderly population is 10%, so this p is equal to 0.1. You can calculate what is the probability that if you randomly select 4 individuals from this population, that exactly 3 of them will be diabetic. And a straightforward way to do this is just by plugging these right into that binomial distribution of where p is equal to 0.1, n is equal to 4, and x, the number of successes, is equal to 3, and you get 0.0036. So this reflects the fact this is only 10% probability. The chance of 3 out of 4 individuals independently having diabetes is quite low. So what is the probability that if you randomly select 4 individuals from this population, that at most one of them will be diabetic? So either 0 or 1. And you can do this just by adding up these calculated probabilities for x equals 0 and x equals 1 to get your total probability of, so the union of these two events of 0, or the union of these two possibilities of there being 0 diabetes cases or 1, and that turns out to be 0.9477, almost 95%. So you see how these rules of probability that we covered are starting to come in handy. Now, what is the probability that if you randomly select 4 individuals from this population, that at least one of them will be diabetic? And let's see, this didn't come out on the slide here, but I'm going to just draw it in. So we calculated on the previous page at most one, and that was 0.9477, so that we could do this by calculating the probability of 2, 3, and 4, but the easy way is just going to be 1 minus 0.9477. Let's see, 1 minus 0.9, let's just call it 0.95, equals 0.05. So you can also do this with the binom.dist function in Excel, and I have used that function in the spreadsheet I've given you. So the binomial distribution not only looks like a normal distribution, but it is in fact very close to a normal distribution. It's not exact, but for reasonably large sample sizes, it is pretty close, and you can approximate it, and this is useful for instances where the predicted number or the expected number of successes in a trial is something more than, let's say, 5. But widely applicable, and in cases of large samples, much easier than doing the exact binomial calculation. So the approximation is a normal distribution with a mean of the number of trials times the probability of success in each trial. So for the 100 trials with a 50% probability of success, the mean is 50%. And a standard deviation, which is the square root of all of this. I'll just extend this over so that's obvious, of n times the probability of success times 1 minus the probability of success. So for example, if we sampled 1,000 individuals where there's a prevalence of diabetes of 0.1, so 10%, then we expect n times p, sorry, that would be 0.01. This is just 0.1, and this would be about 100 individuals in the sample will have diabetes, and the variance would be 1,000 times 0.1 times 0.9, and the the standard deviation, the square root of that. So when the number of trials is large, this approximation is very good. And if these products NP and n times 1 minus p are both at least 15, so that is the expected number of successes and failures. This is just one rule of thumb. Then you get a distribution in the binomial that matches pretty closely to the normal distribution. So in summary, the probability notation and calculations are key both to doing direct probability calculations, but to a lot of the hypothesis testing and applications that we will be doing this semester. And for the most part, we will use the normal distribution, the binomial distribution, and this normal approximation to the binomial distribution quite a bit. We will cover a couple of other distributions as well. But remember the new notation, capital Roman X for a random variable, the lowercase for a realization of that random variable, n for the number of trials, p the probability of success of each trial, mu the population mean, standard deviation sigma, and z for the standard normal distribution, or the z-score would be of an individual outcome would be a lowercase c. Those probability calculations and lookups, you should be able to do that for both binomial distribution and normal distributions. However you do the calculations is fine. You won't be required to do it any particular way, but you should be able to do them. And you should be able to do calculations involving the upper lower tails of the normal distribution and the binomial approximation to the normal distribution. Thanks for listening, and I will see you all next week for your exam.